Yeah. Yeah, good morning, good afternoon, good evening, everybody. While the people start rolling in, I'll quickly make introductions. Today, it's wonderful that we have Nigel Clegg, who'll be speaking to us on ultra-deep 3D electromagnetic inversion for anisotropy. Anisotropy is one of those things that we kind of don't really, that we should be treating a lot more in our EM studies. A guide to understanding complex fluid boundaries. So before I introduce Nigel, just a quick mention to those of you who are new to EMinars that you can go onto the MTNet page and find your way to the EMinars page, and there you'll find registration links for upcoming EMinars, and also you'll find recordings, where to go, links to the recordings and prior presentations. A quick advertisement for next week's EMinar. There's Gisa France, transitional domain at passive continental margins, insights into the crustal structure of offshore Namibia from joint inversion of MT and gravity data. Sounds very exciting. But today we have Nigel Clegg, as I said, on ultra-deep 3D electromagnetic inversion for anisotropy, a guide to understanding complex fluid boundaries. A very brief CV about Nigel. You'll have all seen this when you registered. He's the global geosteering domain lead for Halliburton. His career is listed there. I won't read it out because you all want to quickly get to Nigel. He's assumed the present role in 2017, a bachelor's in environmental sciences and a PhD in geology from East Anglia, Norwich. He was a distinguished speaker at SPWLA in 2019 and 2020. So that I'll stop sharing, Nigel, and hand over to you.
Okay, let me just share my screen. Can you see that clearly?
Yep, looks good.
Okay, hopefully the stuff at the top will disappear. So I'm going to talk about a case study specifically. But before I start, I'll give a little bit of a sort of background to the technology in general, to hopefully bring everyone up to speed on people who are not necessarily used to looking at logging whilst drilling tools, or in fact sort of resistivity and inversion of resistivity from these types of tools, because we're specifically looking at wells that are used for the oil and gas industry. And we're talking about inversion for anisotropy, but we're actually inverting both for resistivity and anisotropy. And the anisotropy part of the inversion came in to help balance the geological models. In some environments, particularly where there's a lot of rocks like shales that are very highly anisotropic, if you just invert for resistivity, it can lead to difficulties in producing a model that is a realistic representation. And we're going to look at this in respect to fluids, particularly a complex fluid, and a turbidite reservoir. That's one of those reservoirs where you're getting mass flows of sand and mass erosion events. So this material was previously, or the bulk of the paper was previously presented at the SPWLA symposium. I thank my co-authors for their help with that. But I'm going to first sort of cover a few basics to try and hopefully get you all up to understanding specifically why we're using these sorts of tools and what we're attempting to do when we use these tools. So when we talk about ultra-deep resistivity logging tools, these are part of the drill string behind usually both the bit and the motor that's driving the rotating drilling assembly, and they're divided into multiple subs. So each sub is essentially a piece of metal with a particular instrumentation on it. And the reason we split this up into a transmitter sub and in here 2 receiver subs is because what we're trying to do with these EM tools is look deep into the formation. So EM has been used in geosteering wells, placing wells and understanding the formations around them for many years, but often those were single sub tools only looking a matter of a few meters around the wellbore. Whereas what we're attempting to do with these tools is look out in the region of 100 feet, or in some cases up to 200 feet away. Because quite simply, if we can see something earlier, we can identify what it is earlier, and it helps us make a steering decision early, so we can actually create a much smoother wellbore, or we can map things that we're not even intending to drill with this single well. So often when you're drilling in a target reservoir, there are more than one sand unit, each containing hydrocarbons, and we might drill in one and map a second one at the same time. And by using different subs, we can increase the spacing from the transmitter to those receivers. And that increased spacing is one of the factors that allow us to look deep. And the second factor is that we use lower frequencies. So generally, we're talking from about 2 kilohertz up to about 64 kilohertz with these tools. And those two combined aspects of the tool allow us to actually see deep. So they're used in several different ways. One of the specific ways is to geosteer wells. That's to place the well in the optimum part of the reservoir and remain within that part of the reservoir. So often identifying a boundary that's away from the well path and perhaps tracking that boundary. So in the case of the example we're going to look here, that might be water below us, where you need to stay a certain distance away from that water so that you don't pull that water into the borehole when you're producing. The second one is to map the surrounding formations and fluids, because both formations and fluids affect resistivity, and we're using these tools to map resistivity. And the reason we say map is that you might be identifying boundaries and units that you never cross with the wellbore. So most logging whilst drilling tools that are within the sort of drill string measure things very close by. So things like gamma tools measure your indications of lithology, so shales and sands. We have density and neutron tools that allow us to map the sort of, again, lithologies, but also potentially fluids. And all those tools look very close to the wellbore because of the way they work. But because of the way electromagnetic energy is transmitted into the formation, it goes out away from the wellbore, we can actually use these to map the surrounding formations. So we're getting in that sort of region where we're starting to bridge from the wellbore scale of tools out towards what you can see on the seismic. And most wells are originally planned off the seismic. So we're looking at big structures when we look at those wells, and the shallower tools are then used to give you petrophysical information about what is nearby. These tools allow us to sort of fill in the gap between and see those boundaries at a significant distance from the well path. And then the other option, often these wells are used when we're landing a well. So quite often they will drill a section of the well and stop just above the hydrocarbon bearing zone, case that off, and then start the hydrocarbon bearing zone as a new section. So these tools, because they look so deep, you can identify the reservoir before you ever drill into it and stop above it, and therefore optimize your landing point. So these are the main three reasons that these sorts of tools are used. Now, the second thing to consider is how we're using these tools when we drill. And this is an example of a BHA here. So you have your bit at the front here, sort of rotary steerable assembly. This is what causes the bit to rotate. And then we have a section further back where we have our LWD tools. So in this case, a transmitter and two receivers. And this kind of configuration for ultra deep resistivity tools up till fairly recently has been the standard configuration. So you can see that your first transmitter is about 26 feet behind the bit in this kind of configuration. And here would be our measure point. So this is where I would be getting the information from, but I'd be identifying those boundaries in the region of 100 feet above me and below me, and building up that picture of the geology. Obviously, in this kind of circumstance that I've shown here, where there's a fault, we would not identify that fault until we got close to it. If we're looking at our normal type of model, which is a one-dimensional inversion, and we would be trying to identify perhaps that fault on a near bit sensor, such as a gamma tool. So recent advances have allowed us to move that transmitter forward and place it much, much closer to the bit. And you can see the obvious advantage when we talk about these two configurations. The closer I am to the bit, the earlier I can identify what has happened. So in many cases, when you drill across a boundary like this, a tool near to the bit, like a gamma tool, might tell you that you've crossed the boundary, but you wouldn't know where you are. You could have been faulted up, you could have been faulted down. Whereas a deep EM tool like this would allow us to see those boundaries away from the wellbore and rapidly identify our positions. You can see the advantage of bringing that sensor measure point and that transmitter forward. And essentially, this is where most of the work with this type of ultra-deep tool is done, is in optimizing the position of the transmitters and sensors, optimizing the frequencies that you transmit at to get a clearer picture of the reservoir, to get identification of boundaries as early as possible, purely so that you can identify those changes and make good geosteering decisions. When we're in a well drilling these, we can only make changes of a few degrees at a time. You can't put huge big bends in your well as you're steering. So you need to make those decisions early to be able to make sure that you can actually hit the targets that you're aiming to hit. Now, one of the questions and one of the things that we're going to talk about here is inversion, but the big sort of point is, why do we use electromagnetic inversion? And quite simply, it's because when we're looking at these tools, we're looking at multiple frequencies and multiple spacings. And in fact, if we start looking at resistivity as a whole and we look at the electromagnetic field that we're measuring, we're talking about multiple components for each of these measurements and spacings. And so if we're looking at all of those different log signals, what we need is a good way to quickly accumulate all that data in a format that's easy for people to understand. If I was just looking at a measurement, at best, I might be able to identify that I was approaching a boundary near to me, but I probably would not be able to use that raw log data to understand where the bottom of the reservoir is, or even potentially if there were further units, as in the case here. So when we're looking at electromagnetic inversion, what we're trying to use is the sort of power of inversion algorithms to represent the downhole geology as a model, use the information based on the modeling of the tool to show that that data for that model matches the real data that we've measured. So we can have high certainty that the model that we then present is a clear representation of where our well is within the formations. So very simply, rather than trying to explain to somebody who is not a geologist or a physicist, perhaps, what multiple different logs are telling you, we're showing them a very simple image to show clearly where the wellbore is, where are the units of interest. So in the case here, this is our main target reservoir, but at the same time, we're mapping a second unit that could potentially be exploited by a second well later on. And this is the sort of final result for the majority of the work that will have been published and presented in formats across the world for the last sort of 10 plus years now. And the bottom here is the representation of the inversion data. So this is a one-dimensional inversion. And when I talk about a one-dimensional inversion, the only considerations in a one-dimensional inversion are that there are resistivity changes above or below the wellbore. It does not look in front, behind, or to the sides. And the blue zones here represent low resistivities, and the reds represent high resistivities. So in the case of this, the high resistivity is the target for this well. We want to be in the high resistivity zone. Above the reservoir, this is a shale. Below the reservoir, this is water. So we end up with a complex series of curves representing the information near to the wellbore, giving us detail about the well itself. But this simple image shows very clearly where the well is placed and where the target is. It's quite simple that you can show this to anyone and say, we're in the middle of the big red zone, that's where we want to be. We can see if we start to get closer to the bottom or closer to the top, and therefore we can adjust our well path based purely on this model itself. And a lot of the work that's done with all of the raw data is to prove and to show that this model created by an inversion algorithm is the best representation of the geology. We want to know that the boundaries that we're seeing here that are created by producing models and comparing the real data to that model data is good. If we make a steering decision based on that, we want it to be right. If I think I'm coming down to the bottom of the reservoir and I'm not, then I make a very expensive decision if I steer up away. So these models are QC'd very closely when we do these drilling operations to make sure that we're representing the well path correctly. But this is a very simple scenario. Here we're just looking up and down. We're not considering any kind of complex geology. And as most people who've looked at geology or even just looked at rock face in general can attest, the geology changes in all directions. This is a very simple system here where we're assuming that we have layer cake geology and that any changes to the sides are totally ignored. So the next step from looking just above and below was to start to look at image log data. Now this is another inversion canvas representing again that one-dimensional change, showing changes above and below. And this is an extremely complex reservoir where we see hydrocarbon zones, water zones, back into hydrocarbon zones, then into another water zone. And this is because this is a very old field where they've pumped water in over many years, and we've got flooded areas, and it's all being confined by geological barriers. So all of these breaks in the changes of the inversion are actually where there are faults. Those faults are controlling the movement of the water. And if you look at this kind of environment, it's a really complex representation of where the fluids are. In this case, the geology is a chalk reservoir. So everything is all chalk. It's purely the differences in resistivity here are only caused by the fluids. And as you can see, trying to understand where you are and map this kind of geology is extremely difficult. But it's very difficult when we're looking in one dimension, but we need to consider what could be happening to the sides as well. You know, very clearly people often demark faults like this as a near vertical structure, but in reality these faults are often tilted, and also they can come in from the side. They can be an oblique type of angle, because it really depends on how our well path intersects those fault planes. And these images below are the first sort of step to understanding what could be happening in terms of the faults. These images are like a wrapped round representation of the reservoir. So this represents the top of the borehole. Then we go down to the left, to the bottom, to the right, and back to the top. So it's like unrolling a tube to represent those changes all the way around us. And so if these images were perfectly symmetrical, then that means my changes would only be happening at the top and at the bottom, because the changes would only occur at the top here and at the bottom. But you can see here, most of these images show really skewed or offset results, indicating that these changes that look complicated enough in the one-dimensional inversion are in fact happening to the sides in many cases. So for instance, in this section here, there is water to one side of the well and oil to the other side. And that's the cause of these faults here again. They're coming in at an oblique angle, they're controlling the position of the fluids, they cut across the well bore, and they're controlling how we see that based on these resistivities. But like in the first sort of a circumstance where we were talking about why did we do inversion in the first place, this is a great representation of those changes above and below us. But trying to reconcile these changes and the changes to the side of us, as indicated by the images, becomes quite difficult when the geology becomes quite complicated. So one-dimensional inversions were used quite frequently because they were a good way to represent the reservoir and what was computationally possible at the time. And these images were then used as the next step to give us the sort of key to understanding what's happening laterally. But in reality, it's still very difficult to bring all of this information together when you're drilling a well and your decisions are being made on a minute-by-minute basis. We've got to make these decisions very quickly. We have to explain these decisions to people who may not understand geology and may not understand these sorts of logs. And therefore, again, it still becomes difficult when you're trying to reconcile three-dimensional geology with disparate pieces of information. And this is why we then sort of transitioned from just looking in one-dimensional inversion to actually full three-dimensional inversions. Because the data that we get from the ultra-deep resistivity tool is a three-dimensional representation of the electromagnetic field as the tool rotates. So the tool is measuring all of those changes to the EM field all the way around it. It's just we're relying on inversions to try and represent that data. And a 1D inversion is the simplest and easiest route to go. But in reality, when the geology is complex, it starts to break down because a lot of the time the changes are to the sides of us. And in fact, where these one-dimensional inversions assume that the changes only happen above and below, if there is a major change to the side, such as here, where I can see from my image, then the one-dimensional inversion starts to become distorted, because it's working on an incorrect assumption. It assumes that only changes happen above or below, but in reality, this changes to the side. So the dimensionality of inversions becomes very, very important. The type of inversion that we looked at to start off with is a one-dimensional inversion. And those are still very, very useful where we're looking at changes above and below. So we're looking perhaps for changes in thickness of units, perhaps units that are pinching out, but we're looking for changes that are easy to identify in a sort of plane that just exists above and below the well path. Anything that happens along the well or to the sides is assumed to remain the same. So any complexity in the geology is not really handled perfectly by a one-dimensional inversion. It will still give you a reasonable result, and you can still use it to steer even when you're in complex three-dimensional geology. But in fact, it starts to get distorted and starts to break down. And there's a second type of inversion called 2D inversion. And what this does is it assumes that things to the sides remain the same, but it's allowing for changes along the well path. So if we cross something like a fault, and there's a fault as we drill across it, we actually get that included within the two-dimensional inversion. It accounts for that change along the wellbore. But it's still assuming that the geology is perfectly is the same to the sides, and therefore is still not ideal. And then the ideal option obviously is to invert the data in full 3 dimensions. The data is 3-dimensional, so we want to then invert that data in 3 dimensions. So if there is something to one side, or even a sort of one side and limited along the well path as well in its position, we can account for that. Now, the main reason that 3-dimensional inversions were not done at the start is because they are hard to do. They are originally thought to be too difficult to do, particularly in the time frame that we're talking about for an oil and gas well. Because if you're talking about the length of one of these tools being about 100 feet, and you're trying to resolve all of those changes along that 100 feet and to the sides and to the above you, you're potentially talking about trying to invert for hundreds of thousands, if not millions of variables. So it's very difficult to do that computationally and make a decision as quickly as in 5 minutes. You know, when we're drilling, we get data up, we need to make a decision within 5 minutes if that information shows that there's a major change in the geology. My inversion is taking hours or days or even weeks, then it's not going to be very useful. It's no good to come into a well at the end of it and come back 3 months later and say, well, you know, look, we should have done this. You know, the well is already drilled, it's already finished. They won't necessarily re-drill it, so it's going to be very expensive. So we need that information quickly. And this is where 3D was originally thought to be a bit difficult to do, largely because of the computational power, etc., required. But the reason for using 3D and why it's so important becomes very clear very quickly. In many situations, we're often drilling in what's considered a relatively common type of reservoir, like a channel. And the expectation is that obviously a channel, you know, we know it geologically, is not going to be cooperative and just exist in the same plane and same position as our well. Quite frequently, we can easily drill out of the side of a channel. When we're drilling, if we're just looking in one dimension and we're looking above us and below us, all we would be able to see is that we have drilled out of the sand. We don't know if the sand continues, we don't know if the sand pinched out, but we would have no idea of where that sand is placed. If we look at a plan view, so looking down from above rather than the side view here, then you could see quite clearly we could just be that the sand is a channel that has meandered off to the side. And that if we look just above us and below us, we totally ignore the fact that our sand has actually just drifted off towards the right. And if we steer our well towards the right, then we could potentially remain within that sand. Now, this is really important use of 3-dimensional data because it allows us to not make mistakes. So the mistake here could be that you've exited the reservoir, and then you could spend days chasing the sand, drilling to one side, then drilling to the other to try and find it again. Or we could look at that data in 3 dimensions and see very clearly where that sand has gone. So I have a video here. Let me stop the laser. So this is that same scenario. And this is the example that you'd see. There's the well in the middle of the channel. And you can see very clearly that the channel starts to deviate off towards the right, and we could easily have changed our well to steer after that sand. Obviously, in the plan here, we just drill out to exit. But you can see how that data can be used, both in terms of steering within a well or identifying other sand bodies. A similar sand body would appear off to the side if it was positioned there. So we can consider the sort of reservoir in 3 dimensions. And that gives us a really powerful tool to steer these wells and to place them in the correct formations. If we look at a similar scenario, so here it looks like the same scenario, but in fact, that reservoir has actually pinched out this time. And if I'd just drilled and then carried on drilling, looking for the sand, I would spend a long time and a lot of money hunting a sand that no longer exists. And the same scenario looked at in a similar way to the well we just looked at would show that that sand gradually pinches out. So you can see why 3-dimensional inversion for resistivity was brought in and why we were using that information to be able to steer wells or map wells, but in a much more sophisticated way than when we were looking at those 1-dimensional images alone. Now that data can be done in multiple different wells, and we can look at the sort of representation of those resistivities around the wellbore, both in the case of that same well that I showed you where it looked like a single massive sand. When we invert it in 3 dimensions, we get much more clarity, and we can actually see that that massive sand is a series of stacked channels. And those stacked channels actually represent a considerable complexity to the reservoir that is not understood if you just looking above you and below you. We get a lot of erosion in these areas from these turbolites, and we're seeing that those sands are actually creating quite a complex structure. And in reality, some of those channels are isolated. So in the case of the 3-dimensional data here, we have a gas pocket in the middle of an oil reservoir. Now, that doesn't sound particularly serious, but in fact, it causes problems with regards to your production. So being able to run the 3-dimensional inversion and identify these channels allowed us to actually block off this sand. And you can see, you can imagine multiple geological scenarios where understanding what's happening in 3 dimensions, such as these examples here, can really help you see what's happening in your reservoir, both to understand what's happening, but also to steer them better. But this is where the sort of limitations of the original inversion that we were looking at with this 3-dimensional inversion started to show us problems. So originally, when we were looking at the 3-dimensional inversion, we were only inverting for resistivity. And that's all I've shown you here is resistivity, to show where the resistivity is around the wellbore, because it's the resistivity that is the key to the fluids, and it's the fluids that are key to whether a well is profitable or not. But a lot of these wells have large areas of shale that are either intersected by the well or that are very near to the well path. And those areas of shale have a laminated structure, which means that they are very, very anisotropic. So my inversions could actually potentially have difficulty if I am only trying to invert for resistivity and I'm not accounting for anisotropy. And in terms of anisotropy here, we're talking about the difference in vertical resistivity. Resistivity is if you're just looking up, compared to horizontal resistivity, which is resistivity if you're looking a lot sort of perpendicular to the wellbore. And that can make a big difference to the quality of your models. So when the inversion was generated to create these 3-dimensional images, we encountered some areas where the inversion would not work. It struggled to produce a model that looked in any way geological, and certainly that we were able to reconcile with the additional data sources that we were looking at. So we knew that the 3D data was struggling to represent those changes. And this is probably because we're looking in all directions. Now, if I'm just looking up and down, my resistivity is much more simplistic than if I'm looking in 3 dimensions. So to account for those changes in the 3 dimensions, we had to incorporate an inversion for anisotropy with the inversion for resistivity to allow us to see those changes to make a better geological model. And that was the main thrust, that was the main point of it, was to then make a better map of the resistivity. Now, I said the 3-dimensional inversions were proven to be quite, or thought to be quite difficult to do real time. That's no longer the case. It's now possible to do these inversions real time, and even to invert an entire well in a matter of a few hours. And there are a couple of very simple technologies when they're described in this way that allow us to do that. And the first is how you mesh the data. So you can see here, what I'm displaying is what's called an octree mesh. Here's a representation of my well path. So near to the well path, we use very fine meshing. And then as you get further away from the well path, you increase the size of the cubes that are representing that data. So this is a slice through the data. In reality, this is a three-dimensional representation of the data. And that allows us to decrease the number of variables that we need to invert for. If all of the squares were tiny, then we would be talking about millions of variables. But by gradually increasing the size of those cubes as we get away from the wellbore, we're actually decreasing the number of variables. And this works very well with electromagnetic data. Electromagnetic data are show most detail near to the wellbore. That's where your highest frequencies and your smallest spacings give you extra information about what's happening. And as you get further away from the wellbore, the EM data becomes weaker. So to see something further away, it needs to be bigger. You know, if we have something in this cube far away, then that could be detected by the tool, but a tiny dot in the top corner here would not be detectable. So it actually works well with the way the EM tools work, but it allows us to both represent that data in a way that is suitable for our tools, but also in a way that allows us to decrease the number of variables we're inverting for. And then secondly, when we're looking at this, you do not need to look at the entire well in one single go. Rather than try to invert for everything, we break this down into single measurement points. So when the tool takes a reading down hole, it's a single measurement point, and all of those points stacked together represent the whole well. Let me put my pointer back on. So this is the whole well, but that's built up of lots of these single points. And each single point can represent a single frequency for a single spacing. So what I'm doing is I'm breaking one huge big problem into lots of small problems. And obviously, with everyone knowing about how accessible the cloud is these days, that then becomes an obvious candidate for parallelization. We can send each of these individual measure points off individually. Sorry, I had to cough then. Send them off individually to an individual processor. So rather than waiting for a long time to get the results, each problem can be worked on independently, and then the results brought back together to represent the well as we're seeing. And this allows us, when we're doing this real time, to get a result back in a matter of a few minutes. And if we're doing an entire well, to do the entire well in a matter of a few hours. And the way the inversion works, our 3D inversion here, it's a deterministic inversion. So it's using a regularization function to gradually bring our misfit closer and closer to a 0 point or to a low point. You never get down to 0 exactly. So each step of this curve is represented by the model gradually getting closer and closer fit between the model data and the real data. So our first model is a representation of the whole space. Everything looks exactly the same. Then the second model is quite a simplistic representation of a high resistivity block and a low resistivity block. And this gradually gets refined as you get closer and closer to the lowest misfit. Now, this is a slice through the inversion, but in fact, this is a three-dimensional inversion that it's doing. But I'm just representing an individual slice to show you how that model gradually improves. And then what we can represent that data of is to show how close the model is at the end, is my model data and my real data can be plotted together. And ideally for the multiple components, for the two different subs, for multiple frequencies, all of those curves should show a very close match, indicating a very low misfit. And that tells me statistically that my inversion is a good result, and therefore I can actually accept that that model may be a good representation of the subsurface geology. Now, because it's inversion, and because we're comparing models to data, we use several QC steps to confirm that that result is correct. And this is one of the things that I'm going to talk about a little bit when we look at the anisotropy case study here. I can run an inversion and produce a model, but I need to have high confidence that that model is correct. You can get a perfect fit from data, but the geological model may be incorrect or may look odd because it's representing the data fit. It's fitting the data really closely, but it's not giving a good representation of the reservoir. And this is because when we're drilling with these tools and we're looking at the subsurface, there's a lot of different factors that have to be taken into account. Things like noise, etc. The most perfectly fitted model may be trying to fit noise. So you have to allow the model some flexibility, and you have to look carefully at your results to make sure that you're confident that what you've got is representing what you're seeing in the subsurface. So now I'm going to talk about the case study. This is what was presented at SPWLA. And we're going to talk more about the anisotropy rather than just the resistivity. And this is because the anisotropy here is giving us a really good clue as to what's happening in a very complex reservoir. So this is a trilateral well drilled on the Norwegian continental shelf across a turbidite reservoir. So you can see here the black lines are my 3 lateral wells, and this is a representation of the top reservoir. So you can see the complexity that's expected of that reservoir as we drill across it. With a turbidite, because of the way that it's deposited, we can potentially see changes in 3 dimensions. You get both the deposition of the sand as it's dumped in a massive event, as you get the sort of collapse of a slope. The sand gets mobilized, it gets dumped in one place, in a single place when the energy runs out. But then later turbidite events can come in and they can cause erosion. So you can end up with multiple events, multiple channels stacked on top of each other, and also really complex really complex geology showing both changes along a well path and to the sides of a well path. So the expectation with these wells, and this is where we looked at them first, was in the resistivity distribution in 3 dimensions to see how those sand bodies were distributed around each individual well path. And here's a 1-dimensional inversion showing each individual well path. So this is laterals 1, 2, and 3. The pink line here represents my well. The blue zone above represents shales. The blue zone below represents water. And you can see here we've got big sand sections, and then we've got areas where those sands have been eroded. There may be some deformation of this sand. It might have been squeezed a little bit after deposition to sort of create some of these more extreme changes. But you can see there is incredible complexity throughout each of these wells. And this is just when we're looking along the well path in a 1-dimensional inversion. These severe changes can happen to the sides as well as along the well path, leading to a very complex 3-dimensional sand sequence. And this is where our main focus was on when we looked at these wells. In fact, this was something that we published early when we started looking at our 3-dimensional inversions. But what we sort of took for granted, but didn't really think about, was the fact that they were expecting a complex oil-water contact. And that's okay. You know, oil-water contacts aren't always simple. They were expecting a complex oil-water contact, but we never really thought, why are we expecting such a complex oil-water contact? In fact, in the 3rd lateral, in one area, you can see here, there's actually sort of intrusion of water where water has been pushed up into the overlying formations. So something is happening in this data that's showing a model where we have a very complex representation of water and oil. Do we know whether this is correct or not? That's where it starts to become a sort of problem in terms of quality control and understanding my inversions, because we don't drill into the water for many parts of the well. You can see here they steer away from the water because we don't want to drill in water when we're drilling a hydrocarbon or oil well. We want to steer away from it. There are some areas where we cross water, but for many of these areas that show this really complex change, we don't cross the water, so you can't prove that there is definitively water down there. When you talk to people about oil-water contacts and often how sort of these are taught at a very sort of early or basic level, everything is assumed to be quite straightforward. You know that sequence having gas at the top, oil in the center, and then water at the bottom. And this is often represented with nice flat boundaries because each of these fluids settle down over time. So in a reservoir, generally, especially a brand new reservoir, you would expect to see horizontal contacts between each of the fluids. As we start to produce in those wells, then there's the expectation the fluids will move. Both the water can gradually come up here and the gas can push down as well in some cases. So essentially, we're still thinking about those contacts as being fairly horizontal. And there are some areas where you can hear about phrases of things like water coning. So I've done a simple representation here of a vertical well where the water is pulled up as the hydrocarbon is produced and you change the balance of pressures. But these are really simplistic representations of those fluid contacts. And they look nothing like what we just looked at in these wells here. They look nothing like these, particularly when we know for certain that there are no producing wells very close to the areas where we see these complexities. So that this could not be written off as coning effect from a nearby production well because the nearby production well is not close enough to cause this. And certainly this water intrusion does not coincide with what we'd anticipate as being the position of a well. So why are my oil water contacts not like this? Why are they not showing a nice simple flat oil water contact that's really easy to understand and even easier to steer along? Trying to steer along a flat oil water contact is quite straightforward. Once I know what depth it's at, I just keep away from that well by maintaining an offset distance. When we look at some areas of that well, we can see how extreme the changes in that oil water contact are. So here there's an 8 meters TVD change over a 200 meter lateral distance. And again, on the other well, we can see in some areas 100 meter change, 100 meters along the well path is a 5 meter change. Now, this is a really good sand. It's high resistivity. It's very porous. I can see that from both my localized measurements and from the inversion. So there is no real reason why this oil water contact should not flatten off, or at least should show some mixing between the water and the oil. Often when we see wells where water starts to move, you get a sort of gradual change in resistivity, a gradational contact from where you're going from pure hydrocarbon down to pure water. You can see here we've got really good sharp contrasts with going from a very high resistivity oil-filled reservoir to a low resistivity water-filled reservoir. So why is this possible? How is this possible? When we look at the data in a sort of more integrated approach, we start to get an indication of potentially what's happening. And here we can look at some areas where we do cross those features, where we do know that this is definitely water, because I can see that I get very low resistivity whilst I've still got good indications of lithology from my density, neutron, and gamma. So I know I've crossed water here, and I know I've entered a water section here. But why are my boundaries on either side so sharp? And if we look where we have those changes, we're often seeing a little peak on the gamma and a change on the density, indicating that there is a thin shale zone bounding these structures. You can see this on the images as well here. There are thin shales that always seem to coincide with those areas where we cross into water. And shale is a barrier to fluid movements. It's very fine grained. Its laminated structure means the water won't necessarily flow through it, or certainly not in a short time scale. So maybe these thin shales are acting as a barrier to the movement of those fluids. So if those thin shales are protecting the zones here, then maybe there's a thin shale protecting the reservoir where we're seeing those massive changes in its structure. Maybe this is a hint as to what's happening. It's difficult to see that that could happen along such a long section. Why would there be a thin layer there? But it could certainly be key to what's going on. And certainly we can see other areas where we see some lower resistivity and we see some thin clay layers. So these clay layers are quite common. It's to be expected in this kind of geological environment. When you deposit the turbidite, right where your sand gets deposited, that's all in one sort of big block. But if another turbidite happens further away and the sand gets deposited further away, the rest of the fine material, the silts and the clays, stay in suspension for a lot longer. and they can create thin layers or even thin lenses further away. So these might represent other turbidites happening in different parts of the field that have then created these lithological changes. If we look at offset wells, and these are often the sort of simplest way to understand a reservoir, and this is where we were expecting to see the shale above. So you can see here, as I said at the start, that low resistivity above was shale, and below it was water. So you can see here there's low gamma here, so low resistivity, so that is water below and shale above. You can see here, this is a typical representation of how hydrocarbons are represented by resistivity. Generally, in the nicer, sort of cleaner parts of the reservoir, you get very high resistivity. Where we see some siltier sections, or we often see decreases in that resistivity. And then often as you go down towards the water, you see this gradual decrease or a gradational contact down to the water. This is a sort of very traditional representation of what we actually see when we look at the sort of fluid column within a given reservoir. But you can see on this well here, we don't see that gradational contact. We see those increases and decreases associated with lithology, but it's almost like a sort of sudden drop at the bottom here, showing no gradational contact or no mixing of the oil and the water down to the water. And right at that point where we see this on an offset well, there is a gamma indicating a thin shale layer at the bottom of the reservoir. So maybe this is a thin shale that is protecting the reservoir and acting as a baffle to fluid movement. And if this can happen here, maybe that is happening in the early parts of my well, and these shales are causing that complex oil-water contact. So how do I investigate that in areas where in areas of the well that we don't cross one of these shales? How can we look to map to see if there is a shale down there? And this is where the sort of main point of the talk came in that we were talking about anisotropy. If I just invert for resistivity, shale is blue and low resistivity, but water is also blue, low resistivity. So here I don't know. I know from my offset data this is supposed to be shale up there, and this should be water down below. But I cannot tell for certain because this is away from the wellbore. But this is the expected position of the sand with water below and oil and shale above. But when I invert for anisotropy as well, I can see in those shale zones, we get a good representation that the shale is anisotropic. And we see in many areas that we get quite an anisotropic shale. But below the well path, I'm expecting this to be sand, and I'm expecting this to be water-filled sand. Sand should be isotropic, so the RV and RH should remain very similar. But when I ran the inversion, what we see is a very thin anisotropic layer immediately below the well path. Now, it's interesting that this was run for a paper to create some nice pictures, and the thin shale layer at the bottom at the initial parts of this investigation was an annoyance. I ran the inversion to create pictures of the resistivity, but then I noticed that it was telling me that the unit below was anisotropic. I was expecting it to be water-filled sand. So when you're then looking at all the other information that we've worked through, it starts to become quite obvious that perhaps this is a thin shale. But at the first part of the investigation, it was like, well, why? How do I explain that? There shouldn't be shale down there. Certainly not for over 1,000 meters. Why on earth is there a thin shale existing 1,000 meters underneath my wellbore? But if there is a shale there, that could be blocking the movement of water, and that could be what's causing that complex oil-water contact. If I look at that area where we had that sort of 8-meter uplift, this is my resistivity. I've removed all the low resistivity. I've filtered it out. You can see here that our resistivity shows that there's actually a sort of steep change in its position in terms of its depth. So we're seeing the sort of lower part of the well here, and then this high resistivity goes up and away from the low resistivity zone that we thought was water. But when you look at the anisotropy, we can see that actually we're seeing that what is below us there is probably a shale and not a water-filled sand, and that only further away is there water-filled sand. So that 8-meter change that we looked at is in fact an 8-meter change caused by a shale blocking the water movement and protecting the reservoir itself. And that's why these areas have not been flooded by the water as the pressures gradually even out that oil-water contact. That's why the oil-water contact is so complex. There are other areas where we can investigate this, because obviously in that area, as I said, we deliberately steered away from it. So we were never going to cross it. So you can't, even though the evidence is quite compelling, you can't prove it categorically. There's a section of the well where we drilled across a thin shale. You can see here it's very low resistivity. I can see here on my gamma and on my density that that's a shale that I drill through. And when I drill through that, I see an anisotropic response on my inversion, but the actual shale seems to continue underneath the sand, and that is probably protecting this zone here. So you see this belly of the sort of reservoir here. If we were talking about normal water movement, we would have expected this to flatten off based on pressure, and we would not expect to see this sort of complex morphology. So again, we've got compelling evidence that those shales that are being indicated by the anisotropy are protecting the sands, and that's the cause of this water. Elsewhere, where we cross into the water here, it's not always a shale that causes it. There's actually a cemented zone in this section here, and we know that this is different because there's no associated gamma increase, but there is an associated density increase. So there are other reasons why the sand is protected in some places, in this case cementation, but in the majority of the well path it seems to be related to the lithology and specifically the gamma and the shale that we're talking about here. So that big question that we looked at the start, or that I looked at the start when I started investigating this, was that huge water intrusion. So there's a small image here to show it again. That's that water that's pushed up into the formations above. And you can look at this as a one-dimensional inversion here. So you can see here that it's quite clearly pushed up, but it's limited by its movement. And then when we look at the other logs, we can see very clearly that there are gamma spikes associated with both boundaries. You can clearly here see on those density images that there are thin layers, and they match very nicely to those boundaries and also to some other changes within that zone. But very clearly that water has got a shale on either side that is limiting its movement. So this has been caused by pressure pushing water up from below. There has obviously been a break in the barrier to fluid movement here in that shale buffer, but either side that shale is still protecting a lot of the reservoir. So you can see here we end up with this sort of almost spit type looking feature where the sand below is protected by a shale on either side. When we look at the three-dimensional inversion, we can start to see those structures in a little bit more detail, and they match a very nice dipping structure. We can use those density images that I looked at to pick dips, to indicate the dips of the formations, and those fit very nicely with the inversions results that we get from the 3D inversion. And again, with anisotropy, we can see that there is a big change in anisotropy across these barriers, and that again, it's the same argument that we had before, that those shales must be protecting the rest of the reservoir. So the anisotropy here is proving itself beyond just a tool to balance my resistivity model. It's actually showing that it has value in its own right, because in a lot of wells that we drill, we stay away from oil-water contacts. We don't go near to low resistivity zones. And if we don't go near to it, we have no way of knowing if that low resistivity zone is caused by lithology or if it is caused by fluid contact. Elsewhere in the reservoir, there's lots of geological structures. Every single time we look at them, we can see further evidence that matches the sort of hypothesis that we created, that it's generated by the low resistivity below the reservoir is protected by low resistivity shales. We see a series of stacked sands with breaks between those stacked sands, and those breaks are actually thin gamma layers, each one representing a zone where we have a thin shale layer that has high anisotropy. Doesn't match perfectly in all positions, but generally where we cross one of those shales, we see a nice anisotropic value. And that gives me confidence that that section that I looked at the start, where we're potentially suggesting there is a 1,000 meter plus section of shale, that really is there. and that's the cause of this complex reservoir. So it sort of looks a bit like a geological oddity when we talk about this kind of thing, but in fact, this is extremely important information. When you produce oil from a hydrocarbon reservoir, the decrease in pressures cause water to move up because you have to sort of balance that pressure somehow. So the water will push up from below. But if there is a barrier to that fluid movement below, then that water will not push up. It has a big impact for how you look at your reservoir and potentially how you exploit your reservoir further down the line. You know, if I'm seeing changes in pressure in my reservoir, but there is no fluid here to replace that oil that I'm pulling out, then it could cause difficulties in how you actually extract that oil. So it's really useful to know that there are zones there that are not related to fluids, but are related to lithology. Generally, we've used this sort of technology in these wells here, but in other fields, in other regions, quite frequently they have severe problems if they produce water, and they need to know categorically if something below them is water or if it is shale. If they're drilling a well and they see low resistivity below, previously the policy would be to stop drilling, call TD, which is the total depth of the well, and then go and drill another well. If that is water below, that's a good call. But if it's shale below, then potentially they could have actually limited their production from that reservoir. There's potential to actually drill further. If you can use anisotropy like this to indicate the lithology is a shale, or if it's a water-filled sand, that's very, very useful information. So as well as being an interesting oddity when I first discovered this, there's actually commercial value to this, to understanding your reservoir in this way. And this comes back to the advantage of those ultra-deep resistivity tools. They look deep into the formation. They see a long way away from the wellbore where none of our other tools are able to detect changes. It allows us to understand things that we may never have been able to see with our original investigation. So just a quick thank you to the people who allowed me to use this data, IKPP, ConocoPhillips and Lundin, and Computational Geosciences and Halliburton for their assistances with this technology. And you can see, again, just to sort of show it at the final here, it now makes sense as to why complex that oil-water contact is. I mean, this is crazy when you consider those initial pictures that I showed where you had nice flat oil-water contacts. This does not look like it makes sense. It's very useful because in two ways. One, it helps me prove that my inversion results are good, and two, it helps us understand what is happening in these reservoirs in much more detail. Thank you. Do we have any questions?
Well, thank you very much, Nigel. That was absolutely enthralling. I really, you know, it's that sort of game is not something I've ever been in, but just tremendous to see the power and possibilities of anisotropic 3D inversion, and we really need to bring that more into routine use in both academic crustal and mantle studies. Okay, the questions will roll in. We don't have one right now, so maybe I'll pose one if that's okay. And when you're doing inversions in real time, I guess you only actually need to invert for the new data. You've already got what you've previously drilled through, and you've already got your model based on what you previously drilled through. So you've got a resistivity model. Do you hold that constant and then just invert for what you've most recently seen?
Yeah, you use essentially a sort of traveling window. So we always invert the last sort of 10 points. But then as that moves forward, then you sort of lock the model for the previous. You don't want to be re-inverting the entire well every single time.
Yeah.
You can do that. You can run what we call as a batch inversion, where you re-invert everything that you have drilled through so far. But for real time, your real-time inversion would gradually grind to a halt, and you would be getting further and further behind the drilling. And it's really critical to try and keep up with the bit. You know, we say generally a few minutes from getting the data to actually getting a result is what you need to be able to do, because they drill some of these wells very quickly, and if you waited half an hour or an hour for your result, the major geological change that you see would be too late to do anything about.
Right.
And it's where the sort of the main push for most of these has been based on that sort of understanding that if we're looking at it real time, it has to be every few minutes. So that traveling window allows you to do that. And then if you want more detail, then you can go back and do a sort of more detailed inversion involving more processing power, etc., that may take longer if you see something of particular interest.
Right. Yeah. I noticed for quite the example you showed that your the well bore seemed to go at the base of the oil section.
Yes. I should have perhaps mentioned it. In the upper parts of this reservoir, they have gas, and they do not want to produce gas in this well.
Okay.
And so they keep to the lower part because that's where the oil column is. There is no change in resistivity between the gas or the oil, so you cannot see any sort of boundary related to that. But in some areas where they drill up too high, you can see an increased separation of the density and neutron curves, and that indicates that you've penetrated a gas zone. But the majority of these wells that they're drilling currently are aimed to be oil wells. They produce the oil first, even though there is a big gas reservoir there as well.
Right. We have a question from Jacques Charoy. I'll read the question out so it gets in the video record. Hi Nigel, thanks very much for an excellent presentation. Are there other typical use cases of inversion for anisotropy in your experience besides the identification of shale?
For anisotropy, the main indication that I've looked to so far is shale, purely because geologically we understand that the laminar nature of the shale makes it more anisotropic. I can't think of other reasons where you could use it. It's possible that there are, but there are not ones that we've identified so far. Usually we need other information. So that, as I said, the identification of oil and gas requires density and neutron. There does not seem to be any correlation between the anisotropy and gas-filled zones. There are some areas where we see that resistivity is often caused by increased cementation, and that's often tagged to density. But again, they do not seem to show a significant response in the anisotropy itself. It's possible that there is. It's just we've only really started to use this technology in this way, so I don't know of any at the moment.
Thank you, Nigel. We don't seem to have any more questions. Perhaps for a lot of the audience, this is very, very new material, and they don't know what questions to pose. If we don't have any more, then I would like to thank Nigel again for absolutely wonderful presentation. The recording will be available in a couple of hours when Zoom has done its processing of it, and I'll put it up on the MTNet YouTube channel. And if Nigel is willing to make the presentation available, I'll make that available on the MTNet as well. So thank you one more time, Nigel, and we'll see everybody next week.
Thank you.
Bye for now.